Now we're ready to talk a little bit about the idea of the greenhouse effect and global warming. So the Earth is located a certain distance away from the sun, and if we just look at the amount of solar radiation that the sun emits that reaches the Earth, the average temperature of Earth should be around 0 degrees Fahrenheit or minus 18 Celsius, which obviously is not a temperature that sustains life. However, what we observe is the Earth's average temperature is much higher than that at 15 degrees Celsius or around 59 Fahrenheit. The reason is because there are certain gases in our atmosphere that helps to trap heat in the planet, and these are what we call greenhouse gases. So these are naturally occurring gases. They help keep some of the heat, so the temperature on Earth is much higher, therefore allowing life to exist. Some of the most important of these greenhouse gases are listed here: water, carbon dioxide, methane. You remember we've talked about this a few times, CH4. We have nitrous oxide or dinitrogen monoxide. Hopefully you'll know how to write the formulas for that. Ozone, another one we've talked about, and some of these CFCs that we've talked about also in a prior chapter. The amount of energy that comes in from the sun and the amount of energy that's being reflected or emitted back out into space from Earth is what we call the Earth's energy budget. We have a certain quantity of them that stays on Earth. And again, that's normal, right? And so just to explain this idea of a greenhouse in an example of this car in a parking lot, you have heat coming in through the sun's radiation that can enter the car. But if you close the windows, that heat doesn't come out as efficiently as it enters. So over time, the temperature of the car increases by a significant amount compared to the outside temperature where the heat can escape. Here's an example. The temperature outside is actually only 80 degrees Fahrenheit, but temperature inside is 99 degrees Fahrenheit. And this is, just for a 10-minute waiting time. So this greenhouse effect is pretty important to keep Earth temperature at a certain value. The problem now is because we keep using fossil fuels as sources of energy, these burning of the fossil fuels generate carbon dioxide at a much higher rate than what is natural. So as a result, we now have what's called an enhanced greenhouse effect. More heat is being trapped than necessary to keep the temperature on Earth at 59 Fahrenheit. So we now slowly are warming up the planet, and this is what we refer to as global warming. Now we're going to talk a little bit more about global warming later on, but we need to first understand why carbon dioxide, water, methane are these greenhouse gases. Why are they trapping heat? There are other gases in the atmosphere like nitrogen and oxygen, and these do not trap heat. They're not greenhouse gases. In order for us to understand how this works, we need to look at the three-dimensional or 3D shape of all of these molecules. We have to understand a theory that is called VSEPR, which stands for Valence Shell Electron Pair Repulsion Theory. It says that because a molecule has atoms in them and the atoms have electrons in them, the electrons are going to repel each other. Now, the repulsion occurs because electrons have the same charge. They're all negatively charged. The interesting thing that comes as a result of this repulsion is that specific electronic geometries are formed, and that only depends on the number of electron pairs around the atom that you're looking at, which we usually call the central atom. It turns out that balloons is a really good way to illustrate how these VSEPR shapes come about. So if you have two pairs of electrons, it's like attaching two balloons together. If you just do this on your own, you'll find that the balloons automatically will adopt this structure, which we call linear. So anytime you just have two pairs of electrons around a central atom, then you're going to get a linear structure, which just looks like a line. If you have three pairs of electrons, as illustrated by this balloon right here, then they automatically form the shape. We call that trigonal planar. So I'm going to show you this table right here, which has the names. The last one is when you attach four balloons together, then it actually forms this thing called a tetrahedral in 3 dimensions. So the way we draw it looks something like this. Now it's a little hard to see this with the balloon, so I'm going to just scroll down here to show you a molecular model of this. So this top three here are the structures that I just showed you. This is the linear, this is the trigonal planar, and this is the tetrahedral, with the pink atom being the central atom. So here you got the central atom bonded to two other atoms, the white atoms. here the central atom is bonded to 3 others, and then here's the central atom bonded to 4 others. I just want to point out that these structures are not necessarily unique to molecules. You have obviously linear structures in many items, right? A ruler is just one easy example of it. This sign of the car is showing the structure of the trigonal planar. And then this one right here, this is a music sheet holder, shows your tetrahedral structure, right? That's what we call the electronic geometry. So it depends on how many electrons you have around central atom. What we're interested in is not the electronic geometry, but the molecular geometry or molecular shape. That is the actual shape of the molecule. Well, what's the difference? Turns out that not all the electrons you have around the central atom is used for bonding, as you saw when we did the Lewis structure portion of lecture. Sometimes some of those electrons are just lone pairs. Lone pairs electrons are not part of a bond, so they're not really visible in 3 dimension. As a result, what we need to know is how many lone pairs and how many bonding pairs are present in the molecule for us to be able to predict the molecular shape or molecular geometry. Your steps to do this is given right here. You're going to start with your Lewis structure, and then you're going to determine the electron geometry, which is another way of saying the basic geometry. And that's only these 3 right here. So it's either linear, trigonal planar, or tetrahedral. And that depends on how many electron pairs you have around your central atom. So for example, like this molecule right here, boron trifluoride, it has the boron atom in the middle, and then it has 3 electron pairs, right? How do I know? Because there's 3 bonds. That means 3 electron pairs. That tells you the basic shape is trigonal planar. Now, I'm going to go one step further to try to figure out how many of those pairs of electrons are actually bonding and how many are lone pairs. In the case of boron trifluoride, all 3 of them are bonding. Then the name of the molecular geometry is just whatever the name of the basic shape is. So the changes or the variation happens when there's some lone pairs present. So for linear, there's really no possibility of a lone pair. So if you just have 2 atoms, that's also linear. So if you have 3 atoms like this, that's also linear. However, when you have trigonal planar, when you have 3 electron pairs, it's possible that you can have all of them being bonding, or 2 of them being bonding and the last one being a lone pair. If that's the case, you call that structure bent. Here's an example of a bent structure. There's a 3rd electron pair, but that 3rd electron pair is part of this pink atom right here, so we can't see it. But we could see bonds, so we call that a bent structure. The tetrahedral one has 4 total electron pairs around the central atom. They're all bonding, we call it tetrahedral. However, they don't all have to be bonding. So let's say only 3 of them are bonding and 1 of them is a lone pair. We would call that trigonal pyramidal. And if 2 of them are bonding and the other 2 are lone pairs, we would call them V-shape or bent. Okay, so that's the same name as the other one. So this is the structure of the trigonal pyramidal. As you can see that this one, hopefully you can see, is just really this structure with that top one taken out. The reason we take it out is because now that's just a lone pair, so it's just part of that pink atom. And then if we take another one out, then it just becomes the bent structure. Okay, so that's the VSEPR geometry for both the basic shape as well as the molecular geometry of different types of molecules. Okay, so now we want to work through a few examples of how to determine the molecular shape using this VSEPR theory that I just described. I'm going to just do 4 of them and then I'll have the last one for you to work on. Remember, the steps are as follows, so I'm writing it here to remind you again. First thing is to draw your Lewis structure, and then the next thing is to find the electron geometry using VSEPR theory, so it's a pretty specific set of geometry. To determine that, you're going to need to look at the number of effective pairs of electrons around the central atom. So what effective means here is that when you have single, double, or triple bonds, they all just count as 1. So if you have 2 single bonds, it counts as 2 effective pairs. If you have 2 double bonds, that also counts as 2 effective pairs. And then there are specific electron geometry names that you have to memorize based on the number of effective pairs for 2, 3, and 4 pairs of electrons. Once you have the electron geometry, now you're going to need to find the molecular shape, and that depends on the electron geometry. So if your electron geometry is linear,
your molecular shape is also going to be linear. If your electron geometry is trigonoplanar, you have two options. That depends on the number of bonding and lone pairs that you have around the central atoms. Depending on what they are, you're going to have different names for them, trigonoplanar and bent. Same idea here with tetrahedral. Let's try this out. We're going to start with methane or CH4. First thing is draw Lewis structure. To determine Lewis structure, I have to get the valence electrons. So methane has 8 electrons. And then I have to draw it. So this is the structure that I have for methane. What I need to figure out then is how many electron pairs are around the central atom. So carbon is our central atom. You just count 1 pair, 2 pairs, 3 pairs, and 4 pairs. So 4 pairs of electrons means a tetrahedral electron geometry. And then you need to figure out how many of those pairs are bonding versus lone. In this case, we have all 4 of them being bonding pairs. So 4 bonding, 0 lone pair. So the molecular shape is also tetrahedral. Next, with water, we have also 8 valence electrons. The structure of water looks like this, with 2 lone pairs around the oxygen and 2 bonding pairs. But they still add up to 4 pairs. 4 pairs means tetrahedral electron geometry. You have 2 lone pairs, 2 bonding pairs combination. That structure is called either bent or V-shape. That's what I call it here. It's just bent molecular shape. Oxygen is next. Oxygen has 12 valence electrons. When you draw it out, it really just has these 2 atoms connected by a double bond. Because it only has 2 atoms, that's has to be linear because there's no other structure that would fit there. Really no central atom. The answer will just be linear for both electronic and molecular shape. Lastly, carbon dioxide, that's an important molecule, right? 16 valence electrons. When you draw it out as a Lewis structure, it will end up looking like this. The atom of interest is the carbon. That's your central atom. So here, this is where we talked about effective pairs earlier. We have 2 effective pairs. 1 pair right here, 1 pair right here. Okay, so again, double, single, or triple bonds are all counted as 1 effective pair. There's 2 effective pairs means a linear electron geometry. Anytime you have a linear electron geometry, you have to have linear molecular shape. There's no other choice. So therefore, carbon dioxide has a linear shape.